Okay, we'll conclude this subsection with another theorem and a corollary. Okay, so the theorem says that if we have a integrable function and it's integrable on the n-dimensional Euclidean space, the whole space, then the Fubini limit is equal to 0. Okay, so you can think of this as the integrand here is the f of x plus h. It's like you shift the function. So for example, if n equals to 1, and this is the f, you shift this f a little by h. So I'm not drawing it well, but it's just the same shape, but you shifted by h to a new place. And what the theorem says is that if the shift h is approaching 0, then the integral of the absolute error between the two functions is approaching to 0. Okay, so that can be seen as when we take the difference of the two, this probably the difference of them becomes something like this. Okay, and then what it says that the integral here approaches 0 if these two functions eventually aligns. They align when h goes to 0. Okay, so that's intuitively what that means, and we want to prove this rigorously. Okay, so the proof. First of all, we can decompose, because f is integrable. Since f is integrable, we know f equals to f1 plus f2, where f1 is continuous with compact support, and the difference between f and f1, which is f2 right now, the difference of them is actually f2, has an integral less than any given epsilon. Okay, so the integral of f2, which is the difference of f and f1, is less than epsilon. So let's say right now I want it to be epsilon over 4. So here I'm going to let epsilon to be arbitrary. Then I can show that f2 has an integral over the entire Rn less than epsilon over 4. Okay. The next, since the f1 is continuous with the compact support, we know that f1 is uniformly continuous. Okay, let's say let k be the support of f1. Then we know that k is compact. That also means that the measure of k is finite, right? Because a compact set in Rn is bounded and closed, so the measure must be finite. And also f1 is uniformly continuous on k, means that there exists some delta, or say h, such that the f of x plus h minus f of x, we use delta. Let me use delta here. Such that this is less than epsilon over, I want to be 2 times the measure of k. Okay, for all the h less than or h inside 0 and delta. Okay, this is because that f1 is uniformly continuous on this k, so that's why I can show that as long as this h is smaller than the delta, the difference of this 2 will be smaller than this quantity here. All right, so given this, we can show that the integral of f1, integral of f1 x plus h minus f1 x, this integral is equal to the integral on k because the f1 is supported on k. Okay, and then this is the integral itself is less than the epsilon over 2 times mu k. Now you can see why I chose the k beginning, because this is a constant right now. This is a constant, so the integral of this is just a constant times the measure of the area, which is the mu of k, and that eventually gives me epsilon over 2. Okay, so I have strict less than here. It doesn't really matter. Okay, so that's for the f1 part. And how about for f2? We know that the integral of f2 x plus h minus f2 x, because this is defined on the entire n, so I can show that the integrand here is bounded by 2 times f, right? So, or is bounded by the integral of f2 x plus h dx, just using the triangle inequality, f2 of x dx. And I know that each one of them is less than epsilon over 4. So sum of them is epsilon over 2. Okay, and here the reason is because of that. Okay, now I just need to apply the triangle inequality one more time to show that the integral of Rn of fx plus h minus f of x can be bounded by the f1 x plus h minus f1 x plus integral of f2 x plus h minus f2 x, and that is less than epsilon over 2, epsilon over 2, which is epsilon. Okay, for all the h. And here is for all the h in this, and this is also true that for all the h in 0 and omega 0 and delta. Okay, and this shows that the limit of this when h goes to 0, the limit of this integral goes to 0. Okay, so that's the completes the proof. Okay, so if we can review just, I think the intuitively it seems obvious, or at least it seems very reasonable, but you need to know how to prove this rigorously. Now let's consider the corollary of that. It says that the corollary says that if you have a integrable function f, then there exists a sequence of continuous function. I call it gk. Let me call it phi k. Phi k, where each of these functions is compactly supported. Right? Just the support is bounded, such that the phi k converge to f almost everywhere, and the integral of the difference also converge to 0 as k goes to infinity. Okay, the proof is, so we actually can prove if we say we for any fixed fixed epsilon, we can just invoke the theorem which is proved to show that there exists a continuous function g with compact support such that the integral of f and the integral of the difference between f and g is less than epsilon. Let me use half epsilon here because I want to sorry, here it should be simple functions. Simple function with compact support. And the phi k goes to f almost everywhere, and the phi k, the integral of the difference goes to 0. Okay, so to prove that, again, for any epsilon, there exists a continuous function g with compact support such that the difference between f and g over e is less than half epsilon. This is something that we have proved before. And then for this g, we can show that there exists a simple function phi such that the difference between g and phi, so g and phi is less than half epsilon. And the reason is because any measurable function, the integral can be approximated by the integral of a simple function due to the definition, right? So this is where we're going to get this phi, which is smaller than or equal to g, and the integral of their difference is less than epsilon, okay? Because g is the supremum of the integral of such simple functions. Okay, and then combining these two together, we can show that the integral of f and phi, integral of the difference between f and phi, is less than epsilon. Okay, they're all on the e's. Okay, just using triangle inequality. Now, since we can do this for every epsilon, now let the epsilon k to be say 1 over k, then there exists a sequence of simple functions. We call the phi k, such that the difference between f and phi k has the integral converging to 0. Okay, and from here we can immediately say that the phi k goes to f in measure, converges to f in measure. Right? This is something I have been proved several times. The trick is pretty straightforward. So the phi k goes to f in measure, and because it goes to f in measure by the Riemann theorem, there exists a subsequence which is still denoted by phi k. Okay, just use the subsequence such that the phi k goes to f almost everywhere. So it goes to f almost everywhere, and at the same time, since it's a subsequence of phi k, so it also satisfies this, right? And this subsequence phi k is what we're looking for. Okay. By the way, this is one. Each one of them has a finite support. So the support of phi k is finite, is bounded, and that it applies to each phi k in the sequence. So every phi k has a bounded support. Okay, so that's finished the proof here. Okay, so now let's just discuss the. So we have learned the Lebesgue integrals so far, and we have been discussing it for several lectures, because this is the most major important part of the Lebesgue theory. is talk about the integral of Lebesgue, integral of measurable functions. It's a generalization of the Riemann's integrals because on one side, we will show soon later that if a function is Riemann integrable, in the common sense that when the integral is defined over a closed interval, and the function is Riemann integrable, then it must be Lebesgue integrable. That's one thing. The other thing is that we can also show that there are many functions that are not Riemann integrable, but still Lebesgue integrable. And we can use, we're not restrict ourselves to just a standard approach or standard techniques in calculus to find the integral. Instead, we can use many properties of the Lebesgue theory. One of the most important ones we have seen before is using the DCT, dominant convergence theorem, to show the some integral exists or the value of that integral. Okay. But now let's focus on the discussion to or the relation between the Riemann integral and the Lebesgue integral, and how to generalize, why I say that Lebesgue integral is a generalization of the Riemann's integral. The relation between Riemann and the Lebesgue integrals. Okay, so to do this, let's first restrict ourselves to the integral of bounded functions on a closed interval, because this is the standard setup of or standard setting of the Riemann's integral. So we only consider the function f that is defined on a closed interval ab to R, where f is bounded. It's bounded here. Bounded means that there exists M such that f is bounded by M. Okay, or it's bounded everywhere, almost everywhere. Okay, so that's our setup of the discussion in this subsection. Now let's recall the definition of Riemann's integral. Okay, so to define the Riemann's integral, we first consider a partition of the interval I. So consider a partition. We call it delta n. So we'll consider the one-dimensional case. So I use the n here as the number of segments in the partition, not the dimension of the space anymore. Okay, so n is the number of segments. So the a is x0, and the x1 all the way to xn, that is equal to b. So that's our partition. And we define or denote the absolute value of this. It looks like absolute value of this, which means that the maximum length of the segments right now. So it's the xi minus xi minus 1 for I from 1 to n. Okay, so it's just the largest the interval, subinterval here. And now we'll define the upper, I would say the upper sum, means that if we take M I n, the capital M I n, to be the supremum of the function f, where the x is on the subinterval xi is 1 to xi. Okay, to be specific, let's say since we partition into m segments, let's say they are all with a superscript n, just to indicate that there are partition nodes for the partition delta n. So in here, And so that's for the supremum, and easy you can define the infimum, which is the lowercase m, and everything will be the same except that the supremum becomes infimum. Okay, and with this, we can define the so-called Dabong sum, Dabong upper sum, Dabong lower sum. Which is defined as the sum of min of xi n minus xi minus 1, and the I is from 1 to I should say that it's not necessarily partitioned to n segments, so it's kn. For the index n, we partition into kn segments. So here, these should be I from 1 to kn. Okay? It could be arbitrary number, kn, from 1 to kn. And this is the upper sum, and the lower sum is just the same thing with lowercase m. Okay, so you'll know what this means. It's just that we have a function like this, and it's defined over a and b. And what we do is just to make a partition of that, and then we have the x1. This is x0, x1, x2, so on and so forth, up to the last one, which is xkn. And I use the n here, just say that this is my nth partition. And then for each segment, I approximate the function. See here, this will be the m1, right? This will be m0, uppercase m1, lowercase m1. So the Dabong upper sum, lower sum is to use the upper estimate. Sorry. Like this, to estimate the integral. You just take the sum of those rectangles, like this one, plus this one. For each interval, just take the maximum value you can. Okay, so it's upper estimate or overestimate of the integral, and that is upper sum here. And similarly, the lower sum is on every interval, it takes the smallest value. So you have this, and then this, and then this, then this. So this is a low underestimate of the integral. So that's the lower sum here. Okay, and then finally, we can consider the Dabong upper integral and lower integral. It's just taking the limit upper and lower integrals, and that's just taking the limit. So its notation is that the upper integral of f is defined as the limit of this upper sum where this n is going to infinity. Actually, it should be that you just need to make sure that the maximum length of the segments is going to 0. Okay, and similarly, the lower limit is just the same limit with the lowercase m. This is how the Riemann integral was defined. Actually, when we get these upper and the lower integrals, if these two limits both exist and they're equal, then we say the function is integrable. So we say the f is integrable, or is Riemann integrable if the upper integral is equal to the lower integral. And in this case, the integral of f is denoted is defined to be the common value of these two. Okay, that's how we define the Riemann integral. And now let's see. This is quite different from the definition for the Lebesgue integral, as we will focus in this class. And that's reasonable, as I explained before, how we interpret these two types of integrals. And now let's establish a relation between the two. To do that, let's first see let's first give a few new notations. Let first for the partition delta n, we denote this this wx wnx to be the sum of min minus lowercase min times the characteristic function of xi and xi minus 1 and xi. Let's define this. So what this means is, go back to this picture, it means that on each of these intervals, I define that as half closed and half open interval here. And on each of this interval, I define the function value to be the gap between the two. Okay, so you can see that the Wn, so you can see that the gap is non-negative, and it is constant over this interval. It's half closed, half open interval. So this Wn is a piecewise constant function and is non-negative. Okay, piecewise constant and non-negative. Okay, and now again we're going to define another function. Which is called the oscillation of f. So we call this Wf, or you can use omega f, which is defined as this limit. Okay, so let me explain what this is. For every fixed delta, positive number delta, I'm going to look at the ball centered at x with the radius delta, which is essentially just the x minus delta and x plus delta, so we are considering 1D case now. And then over this open interval, let's look at the highest oscillation over this interval. That means the maximum value or supremum value over this minus the infimum value over this interval. Okay, or in other words, we're taking a look at the supremum of this supremum of such kind of differences. Okay, so this is just the largest oscillation you can see over this interval here. And then for any fixed x, we're going to push this epsilon to push this delta to 0. So just make this interval smaller and smaller. So this you can see that this value will decrease as delta decreases, because if delta decreases, we'll be taking supremum over a smaller set. So that means the supremum is supposed to be smaller, or potentially will be smaller, and that is the limit we're looking at. Okay, and this is called oscillation of f at the point x. Okay, the oscillation of f at point x is defined by this. Okay, now you can see the relation between the two. Apparently, the Wn is it converges to this Wf, and also the Wn we saw earlier. If you consider a refinement of this delta n, a partition, then you get another Wn and then you can see that the Wn is non-increasing. Okay, so what I'm trying to say here is that suppose you have another partition delta n plus 1, which is a refinement of Wn of delta n. So it's a refinement of delta n means that originally you have this kn partition, kn points. You have this kn points as the partition of the interval. Then you still keep these points, but you add more points in between. Then you get a refined partition, right? So that's what I mean by this refinement. And then for this one, we can show that the Wn plus 1, which is corresponding to the partition or refinement delta n plus 1, is smaller than or equal to Wn of x. And this can be easily seen since that if we take a refinement, for example, here we add one more point in between, then over each of the interval, so suppose we have this xxi plus minus 1, this xxi, and then we add one more point here, and then I need to consider the sum over this part and then this part. But for each part, I'm taking the maximum value minus the minimum value, or the gap must be bounded by this gap here, because this gap is the gap over the bigger interval. So if you consider the gap, this oscillation or variation over the smaller interval, then this must be smaller, right? So that's why the Wn plus 1 must be bounded by or is smaller than or equal to Wn. Okay, and also, as I just mentioned, the Wn converges to Wf. Okay, it's actually convert to F almost ever. Just in case that you chose the point, that you chose the point that happens to be on one of the partition points. So in that case, you probably not capture the variation at that point, but at least it goes to Wf almost everywhere. Okay, now with this, we can try to explain the relation between the Riemann integral and the Lebesgue integral. Before doing that, there's an important property that we have to realize for this Wf. There are two properties of that. The first property is that this Wf gives us indication if the function is continuous at that point. So what I mean by that is that if f is continuous at x, that means if and only if this Wf, the oscillation of f at x, is equal to 0. Okay, that's the first claim I want to make. The proof is pretty simple. I think probably you have seen this before in analysis, so I will not do this again. But I wrote the proof on the notes, so you can, in case you forget it, you can just look at it. The second claim is more important. Here, I'm going to prove that the Wf, if we restrict ourselves to the open interval, just for now, this is a measurable function. Okay, so this is the proof I'm going to give here because it's related to the Lebesgue measure that we learned before. So the proof is this. To prove some function is measurable, recall the definition. We need to show that for any, we need to show that this or less than t. So less than t. This is the measurable set. Okay, and this means that all the x in A and B such that the omega f or Wf at x is less than t. This is a subset of the interval AB. Okay, I want to show that this is the measurable set for every t. Actually, we can show that this Wf is open. This set is open. It's not just measurable; it's actually open set. Okay, so that is even stronger, and we know since we know every open set is measurable. All right, so how to show this? Let's define or denote the ET to be this set. Okay, you know that we have different ways to write it, either this or the full statement is this. It's all the points on the interval AB such that the omega f of x is less than t. Or we can also write it as the pre-image or inverse image of this, right? Either way. Now I want to show that the ET is actually open set for every t. Okay. Now to show that it's open set, I need to show that every point is the interior point of ET. So now for any x in ET, we know because it's in ET, we know that the WF is less than t. Okay, recall the definition of WF. Let me write this full statement of WF. It's the limit of this supremum. I don't want to use this, write this again. So let's first make a new notation. Also denote the W, the big W, x and delta, to be the supremum of the oscillation or the variation on the ball centered at x with the radius delta. So for every fixed x and delta, I can find out the supremum value here, and that is the W of x delta, capital W. Okay, I use the little f here. So it's capital F, WF, define this. So you can see that the little WF of x is just the limit for delta goes to 0 of capital WF delta. Let me write it more clearly here. Capital F, capital W. Okay, so now because this lowercase the WF of x is less than t, we know there exists a delta 0 such that the capital WF of, yeah, I should say here is x delta. The x delta is less than t for all delta less than delta 0. The reason is that the limit of this as delta goes to 0 is equal to WF. So that means that for delta sufficiently small, I should have this less than t. Or in other words, you can look at it in this way. So say this is t, this is the omega f of x, which are both numbers, right? And then if you know this WF of x is smaller than t, you know that this point will be your capital WF of x delta. So for delta small enough, you know that since for delta going to 0, the capital F goes to the little WF, right? And so that means you can choose delta 0 sufficiently small such that for all the delta less than delta 0, this capital WF is smaller than t. Okay, and because of this, we know the I should say that then for any y in this bx delta 0, there exists a delta y such that because y is a point in this open interval, so I can find, so y is the interior point of this open interval, and there exists some delta y such that the by delta y is a subset of the bx delta 0. Okay, it's also open interval, and it's in a bigger interval. Okay, this delta y could be pretty small, but I know there must be such a delta y. And then we know that the w of y delta, so remember that this is the variation on the ball centered at y with the radius of delta, will be smaller than the w of y delta y, where this delta here is less than or equal to y. I'm going to specify that so later, but the delta is something smaller than delta y. And the reason for this inequality here is because if I consider the variation over a smaller set, then the supremum is potentially smaller. Right? That's why I have this. And also, since the b y delta y is a subset of that, so I also know that this is less than or equal to w of x. So they're all capital WF of delta 0 for all the delta smaller than delta 0. Okay, so I don't need to specify this. I specify it here. Okay, so now with this, we can see that, and this is less than t, and that means we know that the limit of this WF for y delta when delta goes to 0 is going to be less than t, right? Because for all the delta smaller than this, I know this is less than t. So that means when delta goes to 0, this one is less than t, or the limit of that is less than t. And it's less than t in the, and also know that by definition, this is the little wf of y. Okay, the limit is defined as the little wf of y, and this means that the y is also in ET because wf of y is smaller than t. Okay, y is in the ET. And now remember that we pick up any point from the neighborhood of x, and we show that y is here. And that just means that this set is a subset of that. And this is like a ball centered at x with the radius delta 0. So it's a neighborhood of x, and we show that the entire neighborhood of x is in ET. So that means x is the interior point. But x, we chose it as any point. Okay, we chose it as any point. Did I specify that? I should say that for any x being ET. So this implies that the bx delta 0 is completely in the ET. So ET is open, and that also means the ET is measurable. And since it's measurable, we showed before that this WF is a measurable function. Okay, so that's the last property that we need before we move on to show the relation between Riemann's integral and the Lebesgue integral. Okay, so here the theorem states the relation. Suppose f is Riemann integrable. Then f is also Lebesgue integrable, and the integral of f is equal to this. So on the left, this is the Lebesgue integral of f. On the right, this is the Riemann integral of f. And we show that these two will be the same. Okay, and to prove this, let me first show another result. Probably that would be better. Let me keep this result for a moment. I'm going to show this next. Let me first show the other one. Let me first show a sufficient necessary condition for a function f to be Riemann integrable based on our Lebesgue theory. So suppose f is a mapping from this interval to R, then and suppose it is also bounded as we or set up at the beginning of the subsection, then our f is Riemann integrable. So I use this notation just to know it's Riemann integrable over interval AB if and only if, look at the points, the set of points where the function f is not continuous or is discontinuous. So I just look at the set of points where f is discontinuous and look at the measure. I will claim that f is Riemann integrable if and only if the measure of this set is 0. Okay. Let me first show this. Okay, to show this direction, suppose f is Riemann integrable. Okay, it is Riemann integrable means that I should claim this above, because we have showed that the Wn is the variation based on the partition delta n. We have this Wn, right? That's what we define here. Define here. Okay, and we also show that this Wn goes to. We have showed that this Wn goes to f as this n goes to infinity, and the delta n, the partition is the size of the partition goes to 0, or the largest the length is going to 0. We know this is true, and we also know that the integral of Wn I should say it goes to Wf, and also remember that Wn is bounded by on each interval it is bounded by this, but I know that the function is bounded between negative m and m. So these two numbers, the difference of them can be at the most 2m. So that's why the Wn must be bounded by 2m. Okay, so I have two things. One is that the Wn goes to Wf. The second is that the Wn is bounded by 2m. So by the bounded convergence theorem, which is the corollary of the dominant convergence theorem, we know that this two implies that the integral of Wn converges to the integral of Wf. All right? But remember that the Wn was defined here in this way. And you look at the integral of Wn. The integral of Wn is equal to, because it's a piecewise constant, so the integral is nothing but just the sum of this mi minus little mi times the length of the interval, which is xi minus 1. Okay, it's from 1 to kn. So that's actually what the integral is. And then you can, since this is a finite sum, we can separate this term and this term. So eventually this just become the Dabon upper sum for this partition, which is this, minus the Dabon lower sum. Okay, so it's just the upper sum minus the lower sum. All right, and then when n goes to infinity, as we showed, when n goes to infinity, or the delta n, and also delta n goes to 0, we know that the Dabon upper sum goes to this, Dabon lower sum here goes to this. So that's why this one eventually goes to the difference of the upper sum minus the lower sum, okay, as n goes to infinity. And this is what happens to the integral of Wn. The limit is equal to that. But on the other hand, also show the limit of this is this. So this just means that the integral of Wf is just the upper integral minus the lower integral. Okay, and this is on AB, or the interval I. So we know that when n goes to infinity, it goes to both of this and this, and that just means these two are the same because they are both the limit. Okay, they have to be equal. Okay, so that is the thing we're going to use now. Because f is integrable, Riemann integrable, we know the upper integral is equal to the lower integral, and they're equal to the integral of Riemann integral of f. And this just means that the integral of Wf is equal to 0 because it's the difference of the two. So it has to be equal to 0. And now Wf is a measurable function as we showed before, and apparently Wx is non-negative because it's taking as a limit of such kind of thing, and each one of this is greater than 0. And when delta goes to 0, it's still greater than 0. Right? The limit is still greater than 0. So this is greater than 0, but the integral of that is equal to 0. That just means that Wf equals to 0 almost everywhere. Right? We know that if the Wf is greater than or equal to 0 almost everywhere, and the integral of f of x of Wf equals to 0, we know Wf is equal to 0 almost everywhere. Okay, and it's almost everywhere means that we know that when it's 0, it means the f is continuous there. And if it's equal to 0 almost everywhere means that f is continuous almost everywhere. And that means the set of points where the function f is not continuous has a measure 0. And that is this direction. The other direction, suppose this set has a measure 0. And that just means that Wf is equal to 0 almost everywhere, right? Because when it is continuous, the Wf equals to 0. And this equal to 0 means that the integral of Wf is equal to 0. And on the other hand, we know that the integral of Wf is equal to the upper integral minus the lower integral. And this is equal to 0 means that the upper integral and lower integral are equal. And that means the function f is Riemann integrable. Okay, so that's the sufficient necessary condition for a function f to be Riemann integrable. When we use the theory of Lebesgue, we use the Lebesgue theory, it's pretty easy to show this. And I think you know that you proved when you learn calculus or analysis, you know that the function f is when the function has finite many or countably many discontinuous points, then the function f is Riemann integrable. But that is also only a sufficient condition because the set of points where function f is discontinuous is finite or countable means that the measure must be equal to 0. And from here, you know that you can immediately say that the f is Riemann integrable. But this is a sufficient necessary condition. So this is the everything you need. So the set here doesn't have to be countable. It could be uncountable. For example, the contour set is uncountable. And as long as the function is discontinuous over only that kind of set, you can still show that f is integrable. So it doesn't matter what the function f takes, what the value of f is, as long as the set of points where function is discontinuous has this measure 0, then the function f is Riemann integrable. Okay, so this is a very elegant result that we can derive from the Lebesgue theorem or Lebesgue theory. Okay, so that's the proof here. Oh, by the way, I probably forgot to mention that we showed that WF is only measurable over this open interval, but actually you add 2 more points, it doesn't change the result, because every time you will consider this kind of a set, you add 2 more points, or do not add it, it doesn't change the measurability of the set, right? So that's why we can extend the WF to the closed interval, and that we can still get this thing. Okay, and that's the beauty of Lebesgue theorem. Lebesgue theory, if there's something happens on a measure 0 set, then you don't care. It doesn't change the integral or whatsoever. Okay, so that's one result. And then as polynomist, I'm going to prove the next one, this. So now what this says is if the function f is Riemann integrable, then it must be Lebesgue integrable, and also the integral will be the same under the 2 definitions. Okay, the proof is like this. So consider any partition where we have this a equals to x0 and then x1 is equal to b. Okay, let's say this is the partition. Then we know that by Lebesgue theorem theory, we know that the integral of f is equal to the integral on each of these pieces, right? Because each one of them is a measurable set. So I can say that it's just the integral over this. Okay, so now for each partition I showed this, and on the other hand I also know that the xi minus 1 xi of f, because f is Riemann integrable, so I have definition on this subinterval as well, and also on this subinterval I know that is bounded above by the mi, capital Mi of xi minus 1, because on this interval the integrand is bounded above by capital Mi, and it's bounded below by the little mi. And the length of this segment is xi minus 1. So that's why I know this is true. So we know that for each of these segments, I can show this, so I can sum them up to obtain the double upper sum and lower sum. Sum of xi minus 1 xi f, which is bounded by, but remember that previously we have shown that this sum of this interval is also the integral, Lebesgue integral of f, and it's bounded above by this double upper sum. Okay, so we know this is true, and because the f is Riemann integrable, we know the lower sum goes to converge to the same limit as the upper sum. So we know that both of them, we know that this one goes up to the lower integral, and this one goes down to the upper integral. And these two upper integral, lower integral, they are equal. So we know that this the Lebesgue integral of f is actually bounded between these two. But I know that when f is is Riemann integrable, I know these two are equal. And this is in between, so that just means that all these inequalities becomes equalities. And this means that this is the f is also Lebesgue integrable, and the Lebesgue integral is equal to the Riemann integral. Okay, so f is Lebesgue integrable, and also the integral Lebesgue integral is equal to the Riemann integral. Okay. So now that's the I think that's the finish the relation between the Riemann integral and the Lebesgue integral. Okay, and you can see that first of all, the Lebesgue integral is a generalization of the Riemann integration, and also whatever you know about Riemann integrations or the techniques you learn there, you can still do the computation there. You can still show that if it's integrable or not. And once it's integrable, and once you can compute the integral in the Riemann sense, you can just use them in the Lebesgue sense. Okay, so this is a advancement of the integration theory. Okay, that's a major part of the Lebesgue theory that we learn in this class. Okay, so I think that's for the connections between these two types of integrals. And next, we're going to talk about a very important topic about integrations. We all know that we're not just taking integration over a single variable. We often take integration over two or more variables. In that case, we would wonder if we can take the integration over one of those variables first, and then take the integration with respect to the second one, so on and so forth. And this is called iterated integrations, right? And here we're going to talk about the iterated integral under the Lebesgue sense. Okay, so in other words, that means the basic idea is that if suppose we have x and y, we take dx dy. So the question is, if we can take one of these variables first, say I can take this x first, and is this equal to the one that I take y first? I take y first, then x. The question is if these two are equal. And it's very important that the integral satisfies this. Okay, and the Riemann integration doesn't have this property in general, but we're going to show that for Lebesgue integral, this actually holds. Okay, so here's this is why I said this is a pretty important and elegant part of the Lebesgue theory. The iterated integrals actually is also is true. It doesn't matter which one you take integral first, and this is called the Fubini Theorem, and we're going to show that later. I'm going to go towards that. So before that, we have several things to set up. First of all, I'm going to define a set of functions. So I consider functions f defined on the Rn, but Rn can be written as Rp times Rq, because x is our p-dimensional vector, y is a q-dimensional vector. I want to show that, say, I'm considering all non-negative functions right now. So the f here is a collection, or is a set of all the functions f that satisfies, that is defined like this, that is measurable. Okay, definitely we'll consider measurable functions only. such that the following conditions hold. What are these two conditions? The first one is that for almost every x in Rp, remember that x is in Rp, y is in Rq. Okay, for every x in Rp, the f of x dot, this is considered as a function of y only because x is fixed. Okay, for almost every x fixed, the f of x y is a function of y, and it is Riemann integrable on Rq. So this is the one of the properties that this function f needs to satisfy. The second one is that if we denote capital F of f, so this means that I'm going to, for this given function f, I'm going to define a new function capital F, which is a function of x, and define it to be the partial integral of f, which just means that take an integral of f for y only. If I define my capital F like in this way, then the capital F is non-negative and measurable. And it's measurable, but apparently it's a mapping from Rp to R. So when we say measurable, means that it's measurable over this set under set Rp, measurable. Okay, so that's the second one. The third one is that the integral of capital F x dx over Rp, and according to our definition, the capital F can be written as the integral of f over y first dx. So this is exactly this, just by definition. So here this inequality is just because of definition of the capital F, and but what I really wanted is that the integral of this capital F is equal to the integral of the lowercase f over the whole space. Okay, so these are the three conditions for f to be in this set. Okay, so that's I just defined this. And now I'm going to show a property of this set. I'm going to show a property of this set. I'm going to show that this set F is closed under certain operations. Okay. So first statement is if a function is in F, that means if there is a function F that satisfies all these three conditions, or all these three properties, and A is bigger than 0, is a real number bigger than 0, then you multiply this function F by A, it is still in F. So it is closed under non-negative multiplication. The second is that if F1, F2 are both in F, then their sum is in F. The third one is that if F and G, they're both in F, F is greater than or equal to G, or F minus G is greater than or equal to 0 for every x and y, for every point x, y, and also G is integrable over the Rn, then I can show that F minus G is also in F. It's also in this set. Okay, it's closed under difference. If the difference is negative and the G is integrable. And the last one is that if we have a sequence of functions fk, each one of them is in F, fk is non-decreasing to F. That means fk is non-decreasing and they converge to this function f, then we can show that the limit function f is also in this set. Okay, so that's the four properties of this set f. That means it's kind of closed under this kind of these operations. So let's do the proof. The first two are very easy to prove because you can show that if f satisfies all these three properties, then you multiply by a, it still satisfies all those properties. And also, if you have two functions f1, f2, they satisfies all these three. Both of them satisfy these three conditions or three properties, then the sum of them also satisfy that. Okay, so I leave this as a practice to you. I'm going to start the proof of the third one. So let's show that if f and g are both in the set, f minus g is greater than or equal to 0, g is measurable, then how to show that f minus g is in the set. Okay, so to this end, actually the key is to show that, is to use this fact to show that g is defined, is finite almost everywhere. Okay, so to show that, since g is in f, and also the g is measurable over Rn, we know that the fg, remember what this defined. This is defined for every x is defined as the integral of Rq of f of gxy over y. The integral is only over y. Okay, so remember that since g is the g is integrable, so that means the integral of gxy dx dy over Rn. Remember that since g is in the set f, so g satisfies the last property here, and that means this is also equal to the integral of f g x dx over Rp. But since g is integrable, so I know that this one is finite. And that also means this is finite. And remember that this is not negative, it's greater than or equal to 0. And it's finite, that means that this function as a function of x is finite almost everywhere, right? So this means that fg is finite almost everywhere on Rp. Okay, then for any x in Rp where this fg of x is finite, I can see that because fg of x is defined as the integral of g over y, and this one will be finite. I remember that for each x, this g of xy is a measurable function of y, and the integral of this, and it's non-negative apparently, and this is bounded, means that this one here is as a function of y must be finite almost everywhere, right? So gxy is finite almost everywhere. Okay, altogether that just means that g of xy is finite of almost everywhere on Rn. Okay, and that means with this fact we can check to check that f of x, f minus g. Okay, just to check if it has satisfy all these three conditions, because I know that f is here for almost every x. This is then that, and g is a function inside this f, so g also satisfies this. So this is very easy to show for f minus g. Okay, and also this is pretty easy to show for f minus g. And the only thing is that to show this. But since we already have the g as a defined finite almost everywhere, and the last one is also easy to show. Okay, so that's for f minus g.